you want to try some of these in a mixed up order, there is practice problems based on these on Canvas with all the other files there. It's longer than the exam. It's just supposed to be a smattering of some of the problems I think are more important. So most of the exam will be problems. Some of the problems will not be off this practice set. They'll be out of the similar to homework on here, but they'll be all problems similar to homework, most similar to the practice problems on Canvas. I'm sorry, this is such an awful semester. I'll have to say something sometime. A lot of you are freshmen in this class probably, and this is just not what college is like. Usually I have practice sessions where I give an extra lecture in between before the test, and everybody comes by and you get to share, what you're having troubles with and talk to each other, and it's just not the same. A March Madness, everybody's hanging out the doors over at Eskimo Joe's watching the game, and this is not what it's like normally. So I'm really sorry it's such a bad year for everybody. And usually and ask me in person. Very few of you are coming online. It's just a click on the same link you do to get to class if you want to talk to me online, but I know it's not the same, and not so many of you are showing up for that. So I hope everything works out. If you get stuck, do come online, and I can schedule other hours since I'm doing it online anyway. I don't have to stick to just those hours all the time. Uh, all right, so there's my preamble. Today we're going to do some material that's mostly not on the test, but it does use material for the test, and it extends what we had a problem we were trying to do, and I ran out of time. Well, let me remind you. Suppose I have f of x equals the square root of x, right? Uh, and I said, find the third Maclaurin polynomial, P3 of x. I use P3 for polynomial because that's in a lot of other numerical analysis texts and other calculus texts. They like T3 for Taylor polynomial here. So they'll put T and I'll put P, and it doesn't matter. Find P of 3 of x, the third order, meaning of degree 3 or less, polynomial, Taylor polynomial. And let's make this one at x equals 1. Or that is at c equals 1. It's x equals c equals 1 for that. How would you find this one? Right? You got to find a third order Taylor polynomial point. You take the function and plug in the point at c equals 1. So f of 1 is the square root of 1 is just 1. Right? And then you take the derivative of the function. So derivative of x to the 1/2 is 1/2 x to the minus 1/2. And f, the derivative of 1 is then 1/2 times 1 is 1/2. Right? You take the second derivative of the function. Right? And that's the derivative of this one. 1/2 times minus 1/2 is minus 1/4. X to the minus 3/2, right? Derivative of x to the minus 1/2 is minus 1/2 x to the minus 3/2. The two halves together make and the minus make a minus 1/4. So then you plug in x equals 1, you get a minus 1/4 times 1. Right? Now we need the third degree polynomial, so we need derivatives through third order. Right? So take the third derivative is the derivative of this one. Minus 3/2 x to the minus 5/2 times 1/4. Well, minus 3/2 times 1/4 is 3/8. And I have that third derivative, just calculating it quickly. And so the third derivative at the point in question, 1, must be 3/8 times 1 is just 3/8. Now I can write down all the derivatives at c equals 1. I can write down the Taylor polynomial at c equals 1. P3 of x is f of, at c equals 1 is f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared plus f triple prime at 1 over 3 factorial times x minus 1 cubed, right? And if it was the Taylor series, you just go on forever like that, right? Well, this is 1 plus a half times x minus 1 plus a quarter. Let's see, minus a quarter. There's a minus there. It just didn't show up very well. Minus a quarter over 2 factorial x minus 1 squared plus 3/8 over 3 factorial x minus 1 cubed. And you can multiply that all out. I just have to erase this. And the third order Taylor polynomial is 1 plus a half x minus 1 minus an eighth, right? 2 factorial is just 2. Minus an eighth x minus 1 squared plus, let's see, this is divided by 6, so the 3's cancel, and you get 1/16 x minus 1 cubed. There it is. You can multiply it out and put it in standard form. I think usually the book just leaves it like this. I've forgotten which one. I think WebDesign leaves it like this. Any questions on that? Find a Taylor polynomial at an arbitrary point. All you have to do is take the derivatives, plug in the point, and then take f at the point plus f prime at the point times x minus the point plus f double prime at the point over 2 factorial times x minus the point squared, and so on, to whatever degree you need. Now comes the harder question. Now, this is why we didn't have time to mess around with this more. Find the maximum error. Right, this is supposed to be an approximation by a third degree polynomial to the function like square root of x, right? It matches the square root of x at 1. It matches the derivative at 1, the second derivative, and the third derivative. So it's a third degree polynomial, something that looks like this, right? It has at most 2 maxima. It might look like that or like that. Third degree polynomials always look one of these shapes. It might just flatten, or it might go like this, just flatten this way, or it might just go like this, or it might just go like this. That's all the different shapes you can get from the square root, right? So presumably maybe this, or but now we say, suppose we want to estimate p of estimate square root of 1 by this polynomial. I'm sorry, square root of 1.1. P3 of 1.1. Well, you just put 1.1 in, right? And you get P3 of 1.1 is 1 plus a half times, this is 0.1, minus an eighth times 0.1 squared plus a 16th times 0.1 cubed. And so these terms are getting smaller and smaller and smaller because 0.1 is really close. 1.1 is really close to 0.1. So these differences are small, and the square of a small number, cube of a small number, and so on, get smaller and smaller as you go out. I don't think I wrote this one down. Maybe I did. I have the difference down. I don't think I wrote this one down. All right, so 1 plus 0.05 minus 0.01 divided by 8 plus 0.001 divided by 16 gives me 1.0488125. So this is approximately the square root of 1.1. What's the actual answer? The square root of 1.1. This is what you could do if you didn't have a calculator that had square root on it. You could do arithmetic on it instead and estimate this. And let's see. So square root of 1.1 then gives fact 1.0488088. So it's good all the way out to these eights here. 1, 2, 3, 4, 5 significant digits. Uh, so the error then is the difference down. It doesn't. What's the error? So the error, the difference in estimating the square root by this polynomial is very small. Square root of 1.1 minus T3 of 1.1 comes out to be 0.0000365 and some other stuff. It's approximately 4 times 10 to the minus 6, right? I did write that down. Yeah, anyway, that's what I put on here. Now, maybe we didn't, maybe we didn't actually have the square root to see how big the error was. We can actually get a bound on the error. So what was the error bound according to our formula? Right? We have a formula that bounds the error that says it has to be at least this small. Let's leave this here and say that's what it is. What was the error bound? Remember the error bound? Bounds the absolute error, that is the absolute value of the error. The absolute value of the difference, this is R3 of 1.1 is what this is, the difference between the square root and the actual polynomial. But the bound on the absolute value of R3 of 1.1, well, it was supposed to be less than or equal to m over, if you go through the third degree, third order, then you get 4 factorial, m over 4 factorial, absolute value of x minus c, 1.1 minus 1, well, I'll slash it here. These are absolute values, to the 4th power, right? It's the, where m is the maximum over all c in the interval, 1 to 1.1, absolute value of the 4th derivative. So to find the bound, I actually need one more derivative. And what's the 4th derivative? Right? The 4th derivative with respect to x, we take the derivative of the is minus 15/16 x to the minus, okay, yeah, x to the minus 7/2. That's the 4th derivative of the function. Then this is the 4th derivative, just plugging c for x. m has to be less than or equal to, well, what is the maximum value of the fourth derivative if x is between 1 and 1.1? If you think about it, the fourth derivative is minus 15 over 16 times 7 to the plus x to the 7 halves. What's the biggest you can make that quotient in absolute value? Let's put absolute value on here. If x is between, drop it now because I took the minus away. How can you make that as big as possible? Yeah, x to the 7 halves is a growing function, right? It's an increasing function. It's a power greater than 1, power greater than 0. So this is an increasing function. To make this as big as possible, you want to make the denominator as small as possible, so you choose x as small as possible. You put in 1. So this is the maximum value of f fourth of c between 1 and 1.1 is 1 over 15 over 16 times 1 to the 7 halves, right? Maybe I should put it this way. F fourth of c is 15 16 c to the minus 7 halves is 15 over 16 c to the 7 halves. Anyway, so there it is 15 sixteenths. So this bound is 15 sixteenths over 4 factorial is 24 times 0.1 to the fourth. There's a bound on the error, and this says, when I calculated it, I come up with 0.000004. That's pretty good. This one is actually pretty close to the bound. A lot of times the actual error is not so close to the bound, but this one, bound gave you a pretty good actual estimate of the error. So the homework problem wants you to do this: calculate the maximum absolute value of the remainder function, and so you say, well, it's less than or equal to this by the remainder formula, and you can compute it using this kind of analysis. What c makes this as big as possible? This next derivative. Maybe it makes you feel better to know that this stuff in the Maclaurin polynomial is not in the test this time. It'll be on the next test. I don't know if that's better or not, but this is on the homework that's due immediately after the test. We're going to cover it now. Well, some of today's material will be on the test and some of it won't. Just depends on what it is. And then there's this additional comment. You need to memorize these series. I'll just recall again. I know I've written this twice already. But the Taylor series is what? For a function f of x at x equals c. It was the sum n equals 0 to infinity, nth derivative of f at c over n factorial x minus c to the n. That was what we called the Taylor series for f of x. And then what this really is, if you think about it, this is the limit as n goes to infinity of Pn of x is what that really means. You take that Maclaurin polynomial like we were just doing, we did the P3 of x. You could do P4 of x and P5 of x. This is the limit as n goes to infinity, the nth Maclaurin or Taylor polynomial. This is Taylor here. If I put C equals 0, 0, then you get Maclaurin as a special case. All right, so that's what you do in the long run. Now, if you do that for arbitrary orders, some of these, find a formula we had last time. We found the formula for the nth derivative, so we can plug it in and get this in sigma notation, find out the cosine of x actually has this formula by taking this limit of the nth order Taylor polynomial. We said it's the sum n equals 0 to infinity of minus 1 to the n over 2n factorial x to the 2n. You need, you should also know the other form though. A lot of times you just need the first few terms. This comes out to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus plus minus plus on forever. We derived that last time by finding this formula for the Taylor polynomial. This is the formula for the f polynomial. We got that. But now that but it's the same kind of derivation we did there, just with a general formula. Similarly, I'll say if you want, we can derive this one too, just to remind you. Sine of x. Oh, we said not only is this the Taylor series for the function, but because the remainder went to 0, this turns out to be equal to the function. That's why I wrote equals here. I hate fussing with these maths. It's exactly what you don't want to do, right? You put your hand on the doorknob and get the germs off there and then put them up in your face. And sometimes these are counterproductive, but they're very important. Keeps all this stuff pointing right. Range things. But because they're and so, but then the heavy off here, it pushed right through the wind. You know, if they had nothing way up. But COVID, I think, is the reason, the main reason I would say is that when you breathe them out, they immediately become coughing away, right? Oops, can't draw a face. Cough. Then the wind goes way across the room, everybody gets infected. And it stops it here. Then they stay closer, blow it all over the room. You know, uh, if the other person sitting here, uh, I don't know, but I don't think anything is affecting people. That makes a big difference. There's my spiel on COVID virus. It's just for fun. uh, but now we want to compute the rest of these things. Sine of x is sum by a completely analogous computation. And it's like the one we did, it's just we find the general term, right? I think we should do one more of these if you want. Minus 1 to the n, because this alternates sign also, over 2n plus 1 factorial x to the 2n plus 1. So it's almost the same, just replace the 2n with the 2n plus 1. And now it looks like this. It's just 1 degree higher in x each time, and divided by 1 more in the factorial. And you get 1, sorry, not 1, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So you should, this form of calculations of things like the derivative. everybody knows those when they go on to their additional classes. So I'll put stars by the thing to memorize. There's a few series you have to memorize. From the geometric series theorem, remember we did the geometric series? We found out that 1 over 1 minus x is equal to 1 plus x squared plus x cubed. This is the series sum 1 times x to the n. You can just leave the 1 off if you want. N equals 0 to infinity. Easy one that you should also. And then this one. We want to derive one. We derived part of this one. This would be the easiest one to do. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth forever. And this one has sigma notation. Sum n equals 0 to infinity, x to the n over n factorial. You want to memorize those four. Those are the basic ones everybody needs if you use these anywhere else. If you want to try to write it, let's know where the formula comes from. But memorize those four. And there are other ones that are useful, and I really like the book's selection of them. But they aren't as important that you memorize them for this class. If you need them on the test, I usually give them to you, but this semester it's open book anyway. It doesn't matter. But other series that are common that I don't think you need to memorize include these. ln of 1 plus x is 1. Let's see if I remember this one. Minus x. Better be careful. I think it's this. Maybe I better write that right now. I'm not positive on that one. Let me leave it off. Arctangent is another one. And it looks just about like this one, actually. X minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. That one goes on forever. But ln 1 plus x is about arctangent x. Couple more I was just thinking of before class. Hyperbolic cosine are somewhat too. I don't think they're worth writing down. But the point is, if you right, they're all series in x minus 0 powers. Right, so these are all Maclaurin series. Makes them a little easier to write and memorize. And these can be used to get new series. The next topic of the section. If you know these, and by the way, this one only converges for absolute value of x less than 1 and diverges otherwise. You should know that. This one converges for all x, as do sine and cosine. So e to the x, sine x, and cosine x converge for all x. All x on these. Now the object is to derive some new series without having to do these. Let me do the thing I said here. If I want to derive the series for e to the x, what do I get? Just to remind you, at x equals 0, so that I get the, well, c equals 0, so that I get the Maclaurin series. I take f of x is e to the x, we said before. Tells you that f of 0 is e to the 0 is 1, right? F prime of x is e to the x. We said f prime of 0 is therefore e to the 1 is 1, and so on and so forth. F double prime of x is e to the x. So f double prime of 0 is e to the 0, is 1, and so on. And so the Maclaurin series from this, derived just like the square root function we did earlier, then becomes, and it turns out the remainder goes to 0, so it's equal to e to the x. E to the x is equal to f of 0 plus f prime of 0 x plus f double prime at 0 over 2 factorial x squared plus so on and so forth, right? But each of the derivatives is 1. So this is 1 plus 1 times x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. And that's where this comes from, right? That's what this is. I hate this. All right, so that's how every time you do one of these, so you don't have to do so much work. As we just did for e to the x is actually the easy one. Some of the others, it's really hard. This is an easy formula, right? 1, 1, 1, 1. Some of them have harder formulas. Cosine had a slightly harder formula, but not bad. Some of them, it's hard to figure out a general formula when you take those derivatives. They get real messy, lots of terms. You got a product rule or something. In each step, there's another product, and the product rule just expands and expands with each derivative. It's terrible. So some series can be deduced from these without going through and calculating all the derivatives. That's one of the reasons you memorize these. Let's do an example here. One of the series for 1 over 1 plus x squared. Find the series for that and the interval of convergence. How about that? How would I find a series for that? I could do it. I could calculate all those derivatives and with great difficulty come up with a formula probably, but how can I do this easily? You just substitute u equals minus x squared, right? Whatever minus x squared is, I'll call that u. Then this becomes 1 over 1 minus u. I know the series for that, right? By our memorized formula, this is 1 plus u squared plus blah, blah, blah. If I like the sigma notation, I could say this is the sum of u to the n equals 0 to infinity, right? But wait a minute, u is just minus x squared. So I could say this is sum n equals 0 to infinity of minus x squared to the n, which is then just the sum n equals 0 to infinity minus 1 to the n x to the 2n. There's the power series for 1 over 1 plus x squared. Moreover, there's a nice theorem in here. I'll just write it as a note, but the book states it as a formal theorem. This power series is unique if any power series whatsoever, n equals 0 to infinity, cn, let's say an, x minus c to the n, represents f of x equal to f of x on an interval then it is in fact this the Taylor series for that function. There is only one series, right? It's like never see that Highlander series. There can be only one Highlander. There can be only one series, right? Then on an interval, it is in fact the Taylor series. So the Taylor series when it converges on an interval to a function, that's the unique power series. So this is actually derivatives with great labor. I just get this, what I found trivially here. You can also write it like this, right? This is 1 minus x squared plus x to the fourth minus x to the sixth and plus so on, right? Just putting in minus x squared for u. So you can write it like this, or you can write a sigma notation like this. That easy? Those derivatives, right? And there's a whole lot of functions like that. Maybe I should call this one A that we can do. How about this one? B. What if I want a series for x times the sine of 2x? How can I get a power series for that? Now, this is nasty if you calculate the derivatives, right? Because it's a product rule. Every time you take a derivative and there's two terms, it's derivative x times sine plus x times derivative sine. Then you take the derivative again, and there's a product rule again and again. Every step there's a product rule. It's hard to gauge. You take those derivatives with more and more terms in them. But if we use a series we memorized, look what we can do. What can we do? Can you see it? We know the series for sine of x. Let's call this u and say the series for sine of u is u minus u cubed over 3 factorial plus u to the fifth over 5 factorial minus and plus so on and so forth, right? Now u is equal to 2x, so this is x times 2x minus 2x cubed would be 2 cubed x cubed over 3 factorial plus 2 to the fifth x to the fifth over 5 factorial minus so on and so forth. And now you multiply this x in. This is 2x squared minus 2 cubed x to the fourth over 3 factorial. And you can do this. Actually, it turns out within the radius of absolute convergence, not necessarily at the endpoints, but you can multiply series term by term. You can distribute. You can FOIL, I guess you should say. This times this, plus this times this, plus this times this, and this times this. And so you take all possible pairs and multiply them out, and you can do a generalized FOIL for multiplying two series together if they have two different series multiplying. Like if you have sine x times cosine x, you could write out the series, write out the series for this one. And multiply this times this, plus this times this, plus this times this, plus this times this, and this times this. And you take each possible pair and add them, multiply them all together, group the like powers. What a mess. Make that a lot of you recognize this, which is, and I know a series. There it is. I just put u equals 2x in, and I could just, it'd be a lot easier to do this series. To multiply them term by term. And within their radius of convergence, they get you the right series. So there's hard ways to do things is the point. And there's easy ways. Here's the way you want to do this one. You don't want to calculate all those derivatives. Just multiply this out. Now this one times this one is a minus, let's see, plus 2 to the fifth x to the sixth over 5 factorial minus so on and so forth. There's the series, and you can figure out from the pattern what the Maclaurin series is, right? This looks like sum n equals 0 to infinity. We could start at 1, might be easier, but it's the powers of 2 are increasing 2 at a time. So it's 2 to the 2n plus 1, right? So I put in n equals 0, I get 1. When I put in n equals 1, I get 3. N equals 2, I get 5. But if you put 2n plus something, then it increases in 2's. And then x is 1 power greater than that, so it's x to the 2n plus 2 all over let's see, n equals 0, n equals 1, n equals 2. These powers are increasing by 2, so it looks like, in fact, these are the same as these, so it's 2n plus 1 factorial. You can write it like that. You can kind of figure out once you write this, figure this one, but you can also write this multiplying. And then finally, we mentioned of these things is taken term by term. And the integral. So the derivatives and the integral of a function f of x equals a power series, sum a on x to minus c to the n. We wrote this before, but I'll just remind you. Exists within the radius of convergence. Same radius of convergence as the original function. And by term integration or differentiation, then you have a plus c from the integral. So for instance, suppose I have this. Here's example C. What's the series for x squared over 1 plus x cubed? I wonder what series. Actually, let's do this one. No, let's do that. X squared over 1 plus x cubed. How can I get that? Oh, this squared. That's what. Yeah. All right, how can I get that? You notice this, right? This looks like the derivative. If I took the derivative of 1 over 1 plus x cubed, I get minus 1. But you can say this is the derivative of 1 plus x cubed to the minus 1 is minus 1, 1 plus x cubed to the minus 2, times the derivative of 1 plus x cubed is 2x or 3x squared, right? So this would be minus 3x squared over 1 plus x cubed. There's a problem like this, by the way, so write this one down. 1 plus x cubed squared, right? So this looks almost like the derivative. Part is minus 3x squared over quantity 1 plus x cubed squared. Recognizing that this is without a constant of being this derivative, I say, oh, I just multiply this by minus a third and say that this is equal to the derivative of minus a third. 1 over 1 plus x cubed. All right? Old time. And now what you can do is figure this series using the 1 over 1 minus x. I'm out of time, sorry. So rewrite this as minus a third on the outside. The derivative, take the derivative of the series here using the 1 over 1 minus x, 1 over 1 minus u formula, and you can find the power series for this. We don't have time, but maybe we can finish it next time. Next time, or maybe after the break, next time I'm going to do questions on the homework and the review examples, right?